everybody. Welcome to Lecture B for this beautiful day when I have to sit in the basement. So a couple of announcements real quick before we get started. One, you may have seen, I just made a post on Piazza a few minutes ago about some regrading of PA0. I know some of you had questions about that, so please see the Piazza post. Don't post in the chat here. If you have questions, follow up on the Piazza post. Two, PA1, we are now halfway through your PA1 period, a little bit more because your weekend is over. So please get rocking on your PA1 and make sure that you get that done by Friday, if at all possible, so you can get maximum credit. I'm a little bit worried about the engagement we had last week. It was lower than I would like to see. And something I forgot to mention in the A lecture today is mid-semester, strange word to use for week 4, but mid-semester evals are out. You should have all gotten emails about that. Please go ahead and do your mid-semester evals. I will look at every one of them. I always look at every one of my evals. And I often make changes to the course based on good feedback that I get from evaluations. So if there's something that works for you, if there's something that doesn't work for you, if there's something that you would like to see, let me know and we'll see what we can do. I'm actually thrilled that they're doing this in week 4. Usually mid-semester evals, they do so late in the semester that the results don't come back until it's basically time for finals, and there's nothing I can really do with it often in the last couple of weeks. But this is early enough that if there's something we can change, let's do it. Let's make this course better. So please do your evaluations both now and at the end of the semester. Now, I don't normally give any sort of extra credit or anything. I know a lot of instructors will bribe their students into doing evals. I don't do that because basically I feel like if you don't care enough about your education and your educational experience to help improve it, then why should I give you a reward, right? It doesn't make sense. Your reward is you tell me how I can make this course better and I make it better. So please do your evals. Now, we left off on Friday talking about hexadecimal, and now I want to continue talking about hexadecimal. Then we're going to talk about integer representations, and I really hope to finish this up today. I managed to finish in a lecture. I hope we'll finish in this lecture as well so that we can start with floating point on Wednesday. This set of slides is pretty dense, so please do follow up with questions. If you have them, you may need to look at this material more than once. There is a really fantastic coverage of this material in your computer systems textbooks, so please take a look at that as well. Now, the beautiful thing about hexadecimal from our point of view when doing systems programming is that it... Nope, that's wrong. Got my pointer in the wrong window. Let's try this again. Is that it divides very cleanly by bit boundaries. So every hexadecimal digit, which runs from 0 to 15, represents exactly 4 bits because 0, 0, 0, 0 is 0. And 1, 1, 1, 1 is 15. So if you have a hexadecimal number, it is very easy to determine, relatively speaking, to determine what the bit value is at any bit position in that entire number. And likewise, if you have a binary number, it is very easy, relatively speaking, to turn that binary number into hexadecimal in a way that is not true for decimal. Now, there are other bases that you will see occasionally. Octal is one of them, which is base 8, which have the same property. Octal is 3 bits, right? Hexadecimal is 4 bits. And it's because the base is a power of 2. So 16, base 16 for hexadecimal is 2 to the 4. And so therefore it divides up very nicely onto these bit boundaries, whereas decimal is the prime factorization of 10 is 2 and 5. So 5 is not representable as any multiple of 2, and so therefore we have this ugly thing where a decimal digit is like 3.5 bits, right? So we don't get this nice even partitioning. So what you need to take out of this table right here is that the hex digits, first of all, represent these 4-digit values, but furthermore, the digits 0 through 7 all have a leading 0 bit, and the digits 8 through F all have a leading 1 bit. And we're going to use this sum later in the lecture, and it will show up on your lecture quiz. So this being able to identify the value of the highest bit in a number, it turns out is going to be valuable to us. So now that we've talked about hex, we'll get back to it here in a minute. We'll use it some here in a minute. I want to talk about why integers aren't as easy as we would hope that they are in computer systems. So you would think that a number which, is an integer would be, relatively easy. But I said last week that it turns out it's more complicated than it should be, and here's one of the reasons. There are 5 basic integer types in the C programming language: char, short, int, long, and long. And their relationships are somewhat complicated. They are defined by these 2 partial orderings that are defined on this slide right here. So every integer type in the C programming language, this post is going to drive me crazy. I'm going to move it over here. Every integer type in the C programming language is at least 8 bits long. And every integer type follows this partial ordering. So a char is, a long is at least as long as an integer, which is at least as long as an int, which is at least as long as a short, etc. And they're all at least 8 bits. And then we have some boundaries in here. So a char might be 8 bits, but a short and an int are both at least 16 bits. And an int and a long can be as small as, a short int and a long can be as small as 32 bits. So all 3 of these values are somewhere between 16 and 32 bits, but we don't necessarily know exactly how large. And a long and a long might be both 64 bits. A long might be longer, a 32 a long might be shorter. We will get to Indianness. There's a question in chat about Indianness. There are slides about Indianness coming up. So it turns out that if we say long without knowing more about our platform, we don't know if it is 32 bits or 64 bits, or if it's the same as int, or if it's the same as long, or etc., and vice versa for some of these other types. So for example, on our x86 64 system, a char is exactly 8 bits, a short is exactly 16 bits, an int and a long, I believe, are both 32 bits, although a long might be 64. I would have to look it up. And a long, I believe, is 64 bits. But if we were on a different platform, that might be a different, we might have a different case there. Actually, I'm pretty sure long, now that I think about it, is, I think this is 32 and this is 64. But the point is, I have to look it up, right? I don't know by necessarily just looking at this. It depends on my platform. And usually that doesn't matter to us. If we say int, we get an integer which is a reasonable size, and we use that integer which is a reasonable size, but occasionally it matters to us just exactly how big these things are. Maybe we're communicating them with another system, or maybe we need to know, for example, that they will hold at least 65,536, in which case we have to have at least 32 bits, or at least 17 bits, but in this case, 32 bits. So on top of that, we can declare our integers with a variety of modifiers. Now, one of them we've already seen, which is const, and there are a couple of others. But we're also going to talk today about signed and unsigned. So we can say, nope, no pumpkin. Don't want to see that word in my chat anymore. There's no pumpkin. No pumpkin. This is actually Lady Grey tea. But we drink our coffee black in this household. That's just how we drink our coffee. If we have a nice latte or a cappuccino, that's fine, but it's just milk and coffee. I was distracted. So signed and unsigned are modifiers that we can put on integers. So we can say signed int or unsigned int, and that will change the sort of range of values that we can store into that integer. Now, if the keyword signed is omitted, and the keyword unsigned is not used, all integer types except char will be signed. So if you just say int x, x is signed. If you say long x, x is signed. If you say char x, x might be signed, but it might be unsigned. On our platform, on x86-64 in Linux, char is signed. However, on other platforms, char may be unsigned. In particular, on PowerPC, char is unsigned. PowerPC is a platform that you aren't as likely to encounter now as you would have just a few years ago, but it's actually the platform that Apple Mac computers were from like 1998 or 1999 for like a decade or more before they switched back to x86. Oh, I'm sorry, switched to x86. But prior to that, they were Motorola 68000, which is a truly ancient architecture at this point. PowerPC is still used in high-performance computing in some other places, but it is not necessarily used in on desktop computers. You don't see it very much. Yes, Leslie. Elided means left out. To elide something is to leave it out. So the way these work, there's also the int keyword, which we can leave out for anything but just int. So it turns out that if we say long nanoseconds, that is exactly the same as saying signed long int nanoseconds, because signed is assumed and int can be left out. Now, in normal code, you would see long. In older code, long int, I think long didn't exist, but long int you would see sometimes. You very seldom see it anymore. I don't know why not, but you very seldom see it. And normally if you see the keyword signed, that is a message from the programmer to the next programmer who reads this that the signedness of this value matters. So for example, it may be that you have a whole bunch of unsigns and then one that's signed and the programmer's like, I really need you to notice that this one is signed, right? Or maybe you would assume due to some domain specific knowledge that this integer would be unsigned, but they're using a signed because they want to use negative numbers as flags or something, right? So if you see signed, usually it's a message from the previous programmer and it's worth looking to see why they left it there. But ordinarily you will not see the keyword signed and the int will be left out for anything but int. So this confusion of how big things are they signed, etc., was a real problem in C, particularly for writing portable code. And in particular, once we got to the era when we had in common use 8, 16, 32, and 64-bit machines all available. And so C99, the 1999 C standard, which we're using, defined the standard int.h header, which defines specific integer sizes that you can ask for by a number of bits. So if I say int 32t, what I'm saying is give me an integer which is exactly 32 bits and signed. There's also an unsigned uint 32t, right? You have an int 16t, a uint 16t, etc. And then there's also these types that are minimum width types where you say, I need an integer that holds at least this many bits, but it can hold more. I don't care. Ordinarily, that's when you need a representation that can hold a value of a certain magnitude, but you would actually like for it to compute very efficiently on the current platform. So in particular, there are many platforms for which you might say int least 8t to get an 8-bit integer, and the platform will give you a 32-bit integer, because while it can compute an 8-bit value, it has to do extra work in order to compute an 8-bit value because its native internal representation is larger. It's 32 bits or whatever. Likewise, there might be platforms where you might say int least 32t and actually get a 64-bit integer. We aren't going to use these values, and you don't see them used, the least values, you don't see them used outside of like high performance computing scenarios very often, but they do exist. These values we will use. In fact, in particular, we will use uint 64t in later assignments. So standard, the C99 standard says that 8, 16, 32, and 64 will all be available to you, and you can use all of those in standard code. There are other values that could possibly exist. So you could have like an int 12t or an int 24t or an int 128t, but not all platforms may provide them. In fact, almost none of them are going to provide 12 or 24, for example. But there may be platforms that they're simply non-standard. So we're now going to look at the representation in memory of some of these integer types. In order to do that, we're going to use a function called dumpmem. And we're going to analyze the dumpmem function in detail in a later lecture. I think the alignment, padding, and packing lecture that's on your course schedule. Excuse me. Apparently I didn't get enough sleep last night. But dumpmem takes two arguments. One is a memory address, and the other is a number of bytes. And then what it does is it prints each of those bytes one at a time in hexadecimal. So if we ask it to print some memory, it will print the hexadecimal values of the bytes of that memory. Don't worry too much about how it's implemented for now, but we're going to look at the results of its execution. So the first thing we're going to dump with our dumpmem is a simple integer. So I have an integer here. I say int x, and I assign it to 98303, which happens to have this hex value, 17FFF. And then I call dumpmem on it. So I give dumpmem the address of x, and I ask it to print the number of bytes that are stored in x, which x is a 32-bit integer on our platform, so it's 4. So it's going to give us 4 hexadecimal bytes. And it gives us FF7F0100, which may be somewhat surprising because the integer that we stored was 17FFF. So let's look at why that happened. So the number 17FFF we can think of as 0x00017FFF, right? We can pad to the left with zeros and we don't change the value. Now, someone asked in the last lecture about this 0x, which I think you should have already seen in K and R. But 0x indicates to the C compiler that we wish to give it a hexadecimal integer. If we give a number that starts with just a 0, so 0, 1, 2, 3 is octal, the octal number 1, 2, 3, which is base 8. 0x, 1, 2, 3 is the hexadecimal number. So this is octal, this is hexadecimal. And then 1, 2, 3 with no preceding digits is decimal. Something on my monitor. You get an alcohol wipe in here. It's going to drive me crazy. There we go. Don't touch your monitors, kids. This 0x just indicates that this constant is hexadecimal. But when I print it out, these bytes, so there's my 00, and my 01 is here, and my 7F is here, and my FF is here. They came out backwards. And the reason is because the order in which we store bits in memory is sort of arbitrary. We decide as programmers, as computer architects, as computer engineers, in what order we store these bytes in memory. And it could be in any arbitrary order. I mean, nothing even says they have to be beside each other. The C standard says they'll be beside each other, but why should they have to be beside each other, right? They could be scattered all over the place. In fact, I'm going to recommend there is, if you Google for the story of Mel. There is a good story about storing bytes all over the place in memory on computers that used to have their memory was stored on a rotating drum. It was like a coffee can that had magnetic media on it, right? And the story of Mel is interesting. Sort of like a music box, right? The story of Mel is interesting. And it talks about leaving data all over the place. But on modern, don't do it right now, I'm talking. But on modern computers, we store our bytes, together in order, but we can store them in either order, right? So 00, 01, 7F, FF, and FF7F0100 are sort of equivalently reasonable ways to store things. And to see this, think about human languages. So in the English language, we write our letters from left to right, starting at the top of the page and moving down the page. But there are other languages that write things differently. So for example, Arabic and Hebrew start at the top of the page and write from right to left from the top of the page down the page. And other languages write from top to bottom. So historically, Chinese, Japanese, Egyptian, etc., wrote from top to bottom. And in fact, some of those languages, like Japanese, write from top to bottom, starting at the right side of the page, moving to the bottom, and then moving to the next column to the left, right? And moving backwards and up and down from the way English is written. There's no reason we couldn't write bottom to top, right? Historically, this didn't happen because of the way that we write. We tend to write from one side to the other and from top to bottom because of the way that we form our letters. But there's no reason we couldn't write from the bottom to the top, right? This is just an arbitrary convention that we have created. And as long as we all agree on how we do it, then we don't have to worry about it. I'm not aware of a diagonal one, but Gallifreyans use circles. So it turns out that there are two reasonable orders that are widely believed or that are widely adopted by computers. And one is where you put the big end of the number first. So these bits here, these 0001 bits, are worth more than these bits down here, right? So as we move this way, our numbers are worth more, right? Because this F is worth, oh, don't make me do math, 250, whereas this F is worth 15, right? So as we move this way, they're worth more. So this is the big end of this number, and this is called Big Indian. Whereas this FF here is worth the least here. So this is the little end of this number, and it is called Little Indian. And these terms actually come from Gulliver's Travels. So in Gulliver's Travels, Gulliver arrives at a location where there is a bloody civil war going on between people who eat their soft-boiled eggs starting at the big end and people who eat their soft-boiled eggs starting at the little end, the pointy end. And so this is where we get this terminology from, which is sort of a commentary on humanity in general, that one would fight civil wars over such things, but as we've seen, these things do happen. And it turned out that this was actually very controversial at one point in computer architecture. Should things be Big Indian or should they be Little Indian? Obviously, they should be Big Indian. Or correct Indian, as we like to call it. But x86 turns out to be Little Indian. And there are Indiannesses that we call Inter-Indian, Middle Indian, or Stupid Indian, or things like that, which are things like where we might have written 0100 7FFF, which is like, this is the highest order, and then this, and then this, and nope. And then this, and then this, right? It's inside out and backwards or whatever. I don't think anything actually uses that order, but there is an order that is sometimes called Nuxie because Unix in that order looks like Nuxie. And so what that is 2143, right? PDP-11s use that for some 32-bit numbers. At any rate, you won't see those these days. These days, you will mostly see either Big Indian or Little Indian. And Big Indian is used by network communication. Oh, I'm drawing behind my face. Yeah, okay, there it is. Big Indian is used for network communication, and Little Indian is used on many modern processors. x86, it's the native Indianness for ARM, although ARM can be either Indian. It's by Indian. It has an instruction that will change it from Big Indian to Little Indian. PowerPC is the same way. But PowerPC defaults to Big Indian, ARM defaults to Little Indian, etc. Anyway, it's more than you want to know about Indianness. So the next thing I want to look at is signs. So we've agreed, or at least I'm asserting, that we can write our bytes in whatever order we want to write them in, but it turns out that we can also, we also have to be able to represent negative numbers, and that has some interesting implications. So for example, if I run this code here, I declare a character C and I assign to it the value 0x80. And then I assign C, the character C, to an integer I. So this is an 8-bit quantity, and this is a 32-bit quantity. And then I dump out all 32 bits of I. Naively, we might assume that this would look like this, which on our platform would print out as, because we're little Indian. But it turns out that I get, in fact, a very different answer from that. On our little platform, or our little Indian platform, we get this answer, which is arithmetically this value down here. So why did we get all these 1 bits at the top rather than the 0 bits that we might have expected? And it turns out that the answer is sign extension, because of the way we represent negative numbers on our computers. So in order to understand how we represent negative numbers, let's first look and see how we represent positive numbers in binary. So this looks a little bit scary. It's in your textbook. There's a great explanation of it in your textbook, but let's talk about it a little bit right now. So if we think of a number as a vector of bits, right? So this is a vector of bits that we're calling x. We've declared int x, right? In this case, uint32 x, say, for example. X has W bits, which we number from 0 to W minus 1, because we are computer scientists or computer engineers, and we love to number from 0, not from 1. So we have X sub 0 down here is our lowest order bit, the bit that's worth the least, and X sub W minus 1 up here is our highest order bit, the bit that is worth the most. So the total value of this bits vector x, so say it was, 0, 1, 1, 1, right? For example, this is x sub 0, and this is x sub 3, and w equals 4. That's a w, I promise. W equals 4, right, in this example. The value of this integer is represented by this summation right here. So we sum all of the bits from 0 to w minus 1, x sub I times 2 to the I. So x sub 0 here is 1 times 2 to the 0. X sub 1 here is 1 times 2 to the 1, right? And each one of these bits is either a 0 or a 1. And 0 times anything is 0, right? So the 0 bits do not contribute to the total sum. And the 1 bits do contribute to the total sum. And if we calculate this out, we would get 7, right? So let's look at that. So if we have the 8-bit binary number 00101011, and this little sub b, or I'm sorry, this lowercase b here indicates that this is a binary number, then the value of this binary number, this positive binary integer, is calculated by this summation right here. So this is just the expansion of that summation form. So because x sub w minus 1, where w is 8 here, is 0, we have 0 times 2 to the 7, 0 times 2 to the 6, 1 times 2 to the 5, etc., on down here, which we can compute, and we ultimately wind up with the value 43. So can anyone tell me what this is in hexadecimal? Just take a moment and convert that to hexadecimal. We have the first answer has come in, and it is 2b, and that's correct, right? So we have a 0 bit, a 0 bit, a 1 bit, a 0 bit, which is the value 2, right? Because 1, 2, 4, 8. Here we have 1, 0, 1, 1. So we have 1 plus 2 is 3, plus 8 is 11, and 11 in hexadecimal is b. So this byte is 2b in hexadecimal, 43 in decimal, and 00101011 in binary. Now, I expect you to be able to do all of those conversions. Binary to decimal, binary to hexadecimal, hexadecimal to binary. Decimal to binary, I expect you to be able to do, but I won't ask you to do it except for clean powers of 2 because it's painful. It's painful to do. Decimal or binary to decimal is also kind of painful too, but decimal to binary is, I'm sorry, binary to decimal is less painful than decimal to binary. What about octal? Octal is base 8. We're not going to use octal. Octal has the nice property that it is in threes, right? So this number here would be 0, 5, 3 in octal, right? So this would be 0, 5, 3 octal. But we're not going to use octal. Octal was very common on 12 and 36-bit machines, which we don't use much anymore. The PDP-11 also uses octal, even though it is a this is a PDP-11 right here. Even though it is a 16-bit processor for reasons that I'm not going to get into right now. Where does the 7 come from? This is an 8-bit integer, which means W equals 8. So this is bit 0, 1, 2, 3, 4, 5, 6, 7. This is bit 7. So 0 times 2 to the W minus 1, which is 7. All right, so that's how positive integers are calculated. Negative integers are a little bit more complicated, and it turns out that there's several ways to handle negative integers, and we're going to look at 2 of them, which we call 1's complement and 2's complement. There's a third that we'll see later in the semester, which is called sign magnitude. We'll see that when we talk about floating point numbers. So, because the numbers stored in the computer are just bits, they're either 0 or 1. There's no such thing as a sign. We can't store a sign. We can only store a 0 or a 1. It must be the case that there is some pattern of bits that tells the computer that we are now using a negative number, right? So there must be some pattern of bits that says this is negative, and some pattern of bits that says this is positive. And the typical ways to accomplish that on a relatively modern computer machine are 1's complement, 2's complement, or sign magnitude. We're going to go through how you calculate 1's complement, how you calculate 2's complement, and then we'll see sign magnitude again when we talk about, as I said, when we talk about floating point. 1's complement is in some sense the simplest representation of a negative number, which is where you take your positive number and you invert every bit. So if it's a 1, you make it a 0. If it's a 0, you make it a 1. So we have a 32-bit 1's complement 1 here, which has a 1 down here, and the rest of these numbers are all 0. We flip every bit. A 0 becomes a 1 in every one of these places, and the 1 becomes the 0 down here. So this is 1, and this is negative 1. Which formally, if we think about our summation right here, so this summation would be this plus the sum from I equals 0 to W minus 2 of x sub I times 2 to the I, right? This is the sort of closed form of this 1's complement negative integer. So this bit is worth exactly, in this case, 2 to the 31, negative 2 to the 31 plus 1, which is 2 billion and something, you know. And each of these remains worth whatever its value was. So 2 to the positive 2 to the I. So it turns out that if we take negative 2 to the 31 plus 1 and we add in all of these numbers, but we don't add in 1, then we get the value negative 1. And that's how a 1's complement integer is represented. So if we look at the 1's complement 4-bit value negative 1, this is how we compute it. So again, this is a binary value. This bit right here is worth 1 times negative 2 to the W minus 1. Again, W minus 1 here is 3 plus 1. So this is worth negative 7. And then these other bits are worth whatever they were worth before, and we add all of this together and we get negative 1. Question in the chat. How does the computer know this is a negative number and not a really large positive number? When you declare your integer and you declare int x or unsigned int My handwriting is terrible, and this application also doesn't keep up with my strokes, which makes it even worse. So when you declare int x, you're saying if it's a really large number and this bit is a 1, I want it to be negative. And here, when you say unsigned int, you're saying if it's a really large number and this bit is a 1, I'm sorry. Yeah, and if this bit is a 1, I just want it to be really large, and it remains positive. And the compiler will emit instructions that cause it to be treated as signed or unsigned. As we're going to see in a minute, one of the advantages of 2's complement is that almost the only time this matters is when you're printing out the values. 1's complement and 2's complement math, 2's complement math with signed numbers and unsigned numbers is the same. 1's complement is not. So this representation, this 1's complement representation, has a little bit of a problem, though, which is that if we do this math and we add up all zeros and we add up all 1s, we wind up with 0 in both cases, because this is clearly 0, right? Because all zeros is 0. But negative 7 plus 4 plus 2 plus 1 is also 0, or as we like to call it, negative 0. 1's complement math has a positive 0 and a negative 0. And they're both 0 because, of course, negative 0 is nonsensical, right? 0 has no magnitude, so it can be neither positive nor negative. And this is a little bit of a problem in certain circumstances. Now, ordinarily, if you have a true 1's complement computer, the processor, when it calculates a negative 0, will store a positive 0 for you. Or in many cases, it will store a positive 0 for you. And if it doesn't, there's also often an instruction that will check to see if something is a negative 0 and make it a positive 0. But still yet, at certain times, as a programmer, you have to care about whether you have a positive 0 or a negative 0. And so this is an inconvenient representation. These days, the most common place that you will see 1's complement math being used is in network protocols. The Internet Protocol in particular uses 1's complement math for computing a checksum on several of its packet fields when you send data. Because the original internet message processor computer, which was, I think, a Honeywell processor of some sort. I should know that, but I don't. I want to say it was a Honeywell 1610, but that may be wrong. Used 1's complement math. And 1's complement actually has some valuable properties for a checksum. But at any rate, we don't mostly use 1's complement math anymore because of this positive negative 0 problem. Now, the other place that you might occasionally see it is in digital signal processing. There are DSPs that still use 1's complement math. For the most part, you will not see it. You will see 2's complement math. 2's complement math does two things for us. One, it makes addition and subtraction of positive numbers and signed numbers that may be positive or negative exactly the same, whereas with 1's complement math, they are not exactly the same. And 2, it eliminates that problem with the 2 zeros. There's only 1 0 in 2's complement math. And the way we accomplish that is, if you remember, in 1's complement, the highest order bit had the value negative 2 to the w minus 1 plus 1. In 2's complement math, the highest order bit has the value negative 2 to the w minus 1 with no plus 1. And of course, after this, we have that same... That is a sigma. By fiat, that is a sigma. We have that same summation that we had before. And what this accomplishes is that it gives us only 1 0. Now, in return, basically what we've done by taking away that plus 1 is we've taken all of our negative numbers and we've shifted them down 1. So whereas 1's complement numbers were symmetric about the number 0, but in return they had a 2 zeros, 2's complement numbers, there's one extra negative number down here and there's only 1 0. So we have an asymmetric number field. So an 8-bit 2's complement number runs from negative 128 to 127, whereas an 8-bit 1's complement number ran from negative 127 to 128. 7. If you look in the textbook, it explains all this, and you can see why that is the case. But it turns out convenient to us to have only 1 0. So if you remember, we looked at 1110 binary in 1's complement, and it turned out that the value of that was -1. In 2's complement, the value of that is going to be -2, because in 1's complement, we had here the quantity of this +1, right? Whereas here in 2's complement, we don't. So we have 1 times -2 to the 3, which is -8, +4, +2, +0, etc., and we wind up with the value -2. So the exact same bit representation was -1 in 1's complement and is -2 in 2's complement. And all negative numbers are like that. In 2's complement numbers, the exact same bit pattern is 1 farther towards the negative, 1 smaller than its 1's complement equivalent. Now, as I said before, almost all machines that you use these days are going to be 2's complement. So, in general, the high order bit of a negative integer is 1. That is not true for all possible integer representations, but it is true for both 1's complement and 2's complement math. So in our previous example, we saw this, where we took a signed character and we assigned to it 0x80, which has the pattern 1000000, which is -128, because the high order bit is a 1. We're using 2's complement math on our machine. And so when we extend this on out, we result in an integer I that is 32 bits long, but still equals -128. We did not change the magnitude of the value, even though we copied 1 bits in, not 0 bits in. And we want to look at why that is. So if we sign extend this, and we copy these 1 bits out here, and we add up all of these values, we're going to come up with the value -128. And it turns out that this is true no matter how many bits we extend in 2's complement notation. So if we look at our 8-bit value, so we have 10000000, this bit has the value -2 to the 7. And these bits all turn out have the value 0. If I make that a 9-bit integer, then this bit now has the value 2 to the 7. All we did was flip its sign because it's no longer the highest order bit. And this bit now has the value -2 to the 8. And it turns out that this value, -2 to the 7, is exactly the same as -2 to the 8 plus 2 to the 7. Because this value is exactly twice this value because we're in binary. We multiply by 2 and we get the next bit. And if I make that a 10-bit integer, then this becomes -2 to the 9, this is 2 to the 8, this is 2 to the 7, and -2 to the 9 plus 2 to the 8 plus 2 to the 7 is still 128. I'm sorry, -128. And I can do that as many times as I want. If I do that 24 times, then I wind up with this 32-bit value where this is -2 to the 31, and each of these is values from 2 to the 30 down to 2 to the 8, right? And then this is 2 to the 7. And if I add all that up, I still get 128, right? If I do that summation. And this works in 2's complement no matter how many bits I extend. Now, I know that's hairy, and I know we covered a ton in this lecture. But I want to say a couple of things to you. One, it's in your textbook. Please look at your textbook. Your textbook explains it differently from how I do. Now, the reason that you have me and not just a textbook is not so that you can ignore your textbook. It's so that you can see this thing in more than one representation and with more than one different explanation. So by reading your textbook, you will see it printed, and you will read one way of explaining it. By coming to my lecture, you will hear me speak it, see me draw it out, etc., and hear a different explanation for how it works. That's actually, and I didn't talk about this in my last lecture, and I should have, that's one of the reasons that I do not use the lecture or the textbook slides. So the textbook author provides slides for the textbook, but they're basically just a cut and paste of the text that's in the textbook. But you can read the textbook yourself, right? By me giving you a set of slides that I created, I am able to give you information that's actually not in the textbook, or is at least written differently than what's in the textbook, and hopefully help you understand it a little more quickly or a little more easily. At any rate, where I was going with this is, if you understand 2's complement sign extension, then you understand essentially everything that you need to understand about integer, binary representation of integers on these machines for 220 and possibly for your entire career, right? So please take a look at computing sign extension. Feel free to go back and watch this part of the lecture again. Please do read it in the textbook. Try to understand sign extension. Even if you don't ever quite grok the beauty of sign extension and why it works the way it does, do go back and look at, in particular, 2's complement representation and know basically what the difference is between 2's complement representation and 1's complement representation. You will absolutely see this again in this course. It will matter to you, and you will see it again in your career. At some point, it will matter to you. So that's it for integer representation. We have like 3 minutes remaining. I'm willing to take any questions that you may have on this or other related topics, but I'm not going to move on to floating point. We'll start with floating point on Wednesday. If there are no questions, then we'll call it the lecture. I will sit here for the next couple of minutes. Okay, so there's a question here. With 2's complement, the gist is that we make the front bit negative. Basically, yes. The first bit, if it is a 1, the number will be negative. And the way we compute it is those summations that we just looked at. And that's true for 1's complement and 2's complement. If the first bit is a 1, it's negative. If the first bit is a 0, it is positive. Now, Leroy, you tell me, after all the talking I did about how you need to read what's in the textbook, whether you think there are any required readings. And then you tell me where you would find those required readings, because there are required readings for essentially every lecture that I do. Programming practices and memory allocation, I think, are the only 2 lectures we've done so far that have not had required readings. I can literally see my heartbeat when I'm quiet in the microphone VU meter on my streaming software, which is kind of cool. With the explicit size, does it make it possible to cheat the sizes of different integers, like make a char larger than its normal size? No, not exactly, because if you declare char, it's still going to be 8 bits, but you can ask for an integer of whatever size you need. And so just because you're ultimately using a char doesn't mean that you have to store it in a char in the interim. So, for example, in one of the early labs, I think we used getchar, which, or maybe it's in one of the exercises in K&R, we used getchar, which stores a character in an integer, not in a character. And the reason for that is to guarantee that it's signed and the guarantee that you have extra bits so that they're able to represent EOF, which is not a valid character, using a representation which is not a valid character. So you can distinguish between the byte that you just read and end of file. So end of file is -1, which will have more bits than the character does. So you can use this trick, yes, but you can't exactly declare a character that's larger. You have to declare it as a different type. So what is the difference between a function returning a static char star and a char star? That actually, so a function cannot return a static. That function is static. A static function is a function that it can only be called within the current C file. It can't be called from other C files. So you could say char star static whatever, and that would be okay too. It's idiomatic to put the static at the beginning, but static modifies the name of the function, not the type that it returns. Okay, it is 5 o'clock. I'm going to go ahead and cut off now. These are great questions here at the end of the lecture. I really appreciate that. And I will see you all on Wednesday. Please keep working on your PA1. Start taking a look at your Lab 4. Thanks a lot. Have a great day. See you Wednesday.